this is 16.4a. We're going to do, again, sticking with the same routine. We're going to talk how to graph hyperbolas. Whoops, hyperbolas. Okay, talk about the key features and everything, and then in the next lesson, we'll take some of those key features and we'll take graphs and then we'll come up with the equations. So we're going to start with the equation, be able to graph it, talk about the key features today, and then tomorrow we're going to take some of the key features or a graph, and then we're going to work backwards and figure out what the equation would have been. So I'm looking at the warm-up and it says draw a quick sketch. So keyword there is just a sketch. So we want to label the 4 vertices, and I put that in air quotes because technically there's only 2. So let's see. The center would be at 0, 0. And then in the x direction, I'm going to go the square root of the number that's underneath there. So I'm going to go 2 in each direction there. And then in the y direction, I'm going to take the square root of that. So I'm going to go 3 in each direction right there. And then I said last week, I kind of like drawing this because it helps me draw a better, call it a potato if you want, but it helps me draw a better ellipse. Okay, now not perfect, and it's tough to draw on the stylus and with the stylus and stuff like that, but that's pretty decent. That's what it would look like. Okay, and then write this down. Don't say anything yet. You need the conjugate of 1 plus radical 41. Luke, what is it?
1 minus radical 41.
1 minus radical 41. Okay, and then Dane, I need the conjugate of 2 minus 2 radical 5.
2 plus 2 radical 5.
Okay, so we know conjugates pretty well. They're pretty easy to find. So I'm going to come down here, and you are going to notice a lot of similarities between the equations, the standard form of the equations of an ellipse and a hyperbola, and also how we graph these. All right, so here's the definition that we can use to derive, which we're not going to do, but how we can derive the equation of a hyperbola. So a hyperbola is the set of points on a plane, the difference, so we'd write the word difference, the difference of whose distances from 2 fixed points called foci is constant. So I realize it's been since last Thursday since we talked about the definition for an ellipse. But for an ellipse, it was exactly the same definition, except for instead of the difference, it was the sum of whose distance is constant. Okay? And it's amazing how one little thing changes what we get. So this little video right here I'm going to show you has a little bit of background. It doesn't derive the formula, but it does kind of show how this would come about. And then we'll talk about the graph-friendly forms. So I'm going to bring this up right here, and I'm going to hit play.
We saw some interesting things about these conic sections earlier. But remember, there's one more conic section called the hyperbola.
Wow.
It looks like 2 parabolas, which are mirror images of each other. But that's not...
Okay. I'm going to pause it right there. Are they actually parabolas?
No.
They are not. They are very different. In the little illustration and the little demonstration that we did with the flashlight, the sides of them do not continue to curve and go up and out. They straighten out. Okay, so they are not 2 parabolas that are back to back.
Not the case. A hyperbola is very different from a parabola. Similar to the other conic sections, it has many interesting properties. For example, the cooling towers of the power plants or the nuclear plants are hyperboloid in shape. But why? A cooling tower should be shaped such that, first, it's efficient in the heat removal process, and second, its structure should be able to withstand heavy wind pressure. Also third, constructing it should be cost effective, that is, building it should require as less material as possible. Hyperboloid is the shape which fulfills all these criteria.
Okay, I'm going to pause it right there just for a second. Raise your hand if you've seen one of these in real life. Okay, they don't have them out in like, we don't have any around here. If you go back east, I think there's some in California, and if you go back east, you see them a lot. When you see these cooling towers, they're very distinctive. One interesting feature of them, has anybody seen one up close? Okay. They're actually on stilts off the ground, so it lets air underneath and then it goes out the top, and then you see steam coming out the top. Okay?
What are the stilts made out of?
Probably concrete or steel.
It increases the cooling efficiency, has
What's that
greater
do?
structural strength, and requires minimum usage of material for construction. Another area where the hyperbolic shape occurs is the trajectory of comets. Some comets in our solar system follow an elliptical orbit around the Sun, and they are permanently a part of our solar system. But a comet traveling at a
I'll pause it right there. Does anybody know where the Sun would be with respect to that elliptical orbit? There's a vocab word. Yeah.
Right there?
It's at one of the foci. Okay, the Sun would be at one of the foci.
a very high velocity such that it can escape the Sun's gravitational pull follows a hyperbolic trajectory around the Sun. Such comets pass
Straight
through our
path
solar
in,
system
curve,
only
and then
once.
straight path out. Not a
Isn't
curve
the
once
hyperbola
it gets
an
out there.
interesting shape? Let's understand what exactly a hyperbola is. Consider 2 points on this plane. Let's denote these points as F1 and F2. Now consider points on the plane such that the difference of their distances from these 2 points is constant. What do we mean by this? Consider this point P. Let's say the difference of its distance from these 2 points is alpha. That is, PF1 minus PF2 is equal to alpha. One thing to note here is that by difference, we mean the absolute value of the difference. That is, distance to the farther point minus the distance to the closer point. That's why the point P, we subtract its distance to the closer point, F2, from its distance to the farther point, F1. Now the question is, are there any other points the difference of whose distances from F1 and F2 is alpha? Yes, there are many such points. The collection of all such points is called a hyperbola. Consider this point Q on the hyperbola. The difference of its distances from the 2 fixed points will be equal to alpha. Since for the point Q, F2 is the farther point, the difference QF2 minus QF1 will be equal to alpha. Similarly, for this point R on the hyperbola, its distance RF1 minus RF2 will be equal to alpha. So a hyperbola is the set of all points in a plane, the difference of whose distance from 2 fixed points in the plane is constant.
Okay, I'm going to pause it right there, and I'm just going to point to P. Hope you can see that on here. There would be another point about right there that would be like a mirror image. Just come straight over here. There would be another point over here that would be like P, just on the other branch over here, and then another one over here. So the 3 points that they've got on here all correspond to 3 other ones. So here's P, here would be another P, there would be another P, and there would be another P. Here's R, there's an R up here, there's an R over here, and an R down here. Same thing with Q, and you can do that with any point you want on any branch of that, okay? So we'll watch just a little bit more.
By difference, we mean the distance to the farther point minus the distance to the closer point. These 2 fixed points together are called the foci of the hyperbola. Notice that unlike any other conic section, a hyperbola is made up of 2 curves which are mirror images of each other. Now here we took the constant difference to be alpha. If we take any other number as the constant difference, we will get different hyperbolas. Let's say we take the constant difference to be beta, which is greater than alpha. Then we will get this hyperbola, which is narrower than the previous one. If we take the constant difference to be gamma, which is less than alpha, then we will get this hyperbola, which is wider than the previous one. So we see that depending on the value of the constant, the hyperbola becomes narrower or wider. Now tell me, doesn't the depth
30, 60, 90.
Okay.
40, 45.
All right. Okay, so back on the notes. Okay, from 16.1, so there are still 2 people who I don't think have turned in the assignment for 16.1. You should have watched that video. It's 10 minutes long. Okay, from 16.1, here's how you can tell. As long as we have all of the terms on one side, or at least the squared terms on one side, you can tell it's a hyperbola just by looking at the equation, because it has 2 squared variables, and those squared variables will have different signs. That's it. It doesn't have anything to do with the size of the numbers that are in front of them. It just has to do with the signs of them, okay? Now, there are two graph-friendly forms of hyperbola. One of them looks like this, and one of them looks like this. Okay, now, you'll notice that these look very similar to the ones for an ellipse, and we do have to have both of them, because one of them has to be positive. We normally put the positive one in the front, and one of them needs to be negative. That's that whole different sign thing. So the positive one's going to go in the front. Maybe it's x, maybe it's y. The negative one's going to go second. Maybe it's x, maybe it's y. But that's how we're going to graph these. So if you have those kind of in your head, just like an ellipse, it just has a minus in it, then here's what we've got. The center is located at h comma k. We find the constant, that's the adjustment with the x. That's going to be the x coordinate of the vertex. The constant adjustment with the y, that's going to be the y coordinate of the vertex. Okay? And then here's why we need two forms. If x squared is positive, the branches open in the horizontal direction, in the x direction, so to speak. And if y is positive, then it opens in the vertical direction. Oops, vertical. Now, these are the parts of a hyperbola that we're really interested in. There's a whole bunch of them with a hyperbola, and some people consider this the most complicated of them. So, they have a center, of course. They have two branches, two parts, two pieces. They have two foci, or you heard her call them foci, I suppose you can say that. And they have two vertices.
Is the foci
Okay.
Foci, remember, is always going to be inside the curved part of the conic section. Okay, so it's not actually on the hyperbola, it's going to be inside the hyperbola. And then it's got a couple of other things. It's got what we call a transverse axis. It's got a conjugate axis. It has a fundamental rectangle. Okay? And really important to the shape are these asymptotes. Okay? So here's what I'm going to do. I'm going to give you just a second to finish writing all those down. And I'm going to show you how to graph one. And then I'm going to run through a step-by-step procedure. And then I'm going to show you, hey, you can either remember this step-by-step procedure, or you can just remember some key principles, and then you'll be able to graph these. Okay? Everybody ready?
Yes.
All right. So I'm going to blow this up, and I'm going to come off to the side over here. And this is what I'm going to do. First of all, I notice that this is a hyperbola because one of them is positive and the other one is negative. I notice that on this, and I'm going to be better about this, I'm going to write a capital C. So the center is at 0, 0. So I know that. Just like dealing with an ellipse, I'm going to look underneath the x term and I'm going to take the square root. So I'm going to go 2 units in this direction and 2 units in this direction. And I'm just going to make a mark, not a point. I'm going to make a mark. Then in the y direction, I'm going to go the square root of 9. So I'm going to go 3. And I'm going to make a mark. Then I'm going to draw a dotted rectangle. So to right now, it's almost exactly what I did to draw an ellipse. Then I'm going to do this. I'm going to go from diagonal to diagonal, from corner to corner, and I'm going to draw a bunch of diagonal dots making a straight line. So you'll notice that it's going to go through the center, and it's going to continue like that. So I need to slide this down just a little bit. I'm going to draw that diagonal, and I'm going to draw this diagonal. And Crew's going to do it too.
Okay.
Okay, now I'm going to change colors and I'm going to start drawing the hyperbola. All this stuff here is just there to help me make the correct shape. Now what I need to look at is which variable is squared. Because the x is squared, because this is positive, it's going to open in the horizontal direction. So the two pieces, the two branches are going to be over here and over there. So this is what I'm going to do. I'm going to start running along one of these straight lines. And then I'm going to come in here and I touch this point right there. Then I keep going and run along that and straighten out. The other branch is over here. So I'm going to run along this straight line, curve around until I hit that vertex, and then come around here and then approach the straight line and continue. And if you would put arrows on the ends of each one of those, then we're in pretty good shape.
Yeah.
Okay, so I've got the center right here. I've got the vertices right here. And then I need the foci. So here's the interesting thing about the foci.
That aren't good.
If they've got to be outside the box, I'm going to use a squared and I'm going to use b squared. Guess what we're going to do with those so that we'll make sure that it's going to be outside the box. Wilson?
Adam.
We're going to add them together. So we're going to do we're going to do a squared, which is 4, plus b squared, which is 9.
13.
And that's going to be c squared. So c is going to be radical 13. Radical
Whoa.
13.
Where's radical 13?
Okay.
Radical.
Radical 13 is about 3.5-ish, somewhere in that neighborhood.
Okay.
So I'm going to go about 3.5 in this direction, so I'm going to put a dot right there.
Oh, yeah.
So this is radical 13 comma 0, and that's one of the foci. And the other one is over here. This would be negative radical 13 comma 0.
Dude, that's light work.
Wouldn't it be?
No, Wilson.
Never mind.
Okay, everybody good?
So I
Okay.
think like that's like the same as
Now, that's how we draw them.
Oh,
Any questions?
No.
Okay. I'm going to come back here and we're going to run through most of what I just did.
oh,
So, if it's in this form, and notice that it is, and x squared is positive, so that one comes first, we're going to take the square root of the number underneath the x squared, and we're going to go that many units in the x direction from the center of the hyperbola. And remember, the center of this hyperbola happens to be 0, 0. And we're going to make just a mark. So we just kind of put a little tick mark. Square root of the number underneath the, this should say y. Sorry about that. Switch that, will you? Will you put a y right there? Sorry about that typo. That's a y. And go that many units in the y direction. And we make a mark. So we made this mark here and this mark here. Then in the y direction, we made this mark here and this mark here. It says use the 4 points you just sketched, or point made to sketch the fundamental rectangle. So this rectangle has a name. It's called the fundamental rectangle. We draw the diagonals of the rectangle and we extend it to the corners of the graph. These are the asymptotes.
Ross, sorry to bother you again. Will you send the bus guard to check out, please?
I will.
Thank you.
Tell her she pronounced your name.
the
Yes,
vodka
driver.
guy.
And there's fewer on this than there are of the others, so I think we're going to do them all. Okay. The branch is open in the direction of the which variable? Did you catch that? The positive one. Whichever one's positive, so in this case, whichever one comes first, because we usually write it that way, it opens in that direction. So it opens in the x direction. It opens in the horizontal direction. Okay? The transverse axis runs in the direction of the positive variable. So I'm going to change colors. We don't often do this, but I'm going to go ahead and draw this is the transverse axis. Okay? So transverse axis. Okay? Cuts right across them. If we go on a transcontinental flight, we go across the ocean, or across the continent. If we do transoceanic, we go across an ocean. Yeah, hustle.
What? I got like a quick question.
Hustle.
Why is like the y, like why does that matter? Because you're not even like crossing that point.
This one up here,
Yeah.
it's used to make the asymptotes.
Ah.
Okay,
Yeah, I
you'll
knew
see
that.
why in just a second and why they're important. Okay, so the transverse axis runs in the direction of the positive variable. The vertices are where the transverse axis meets the fundamental rectangle. So that's these guys right here. Okay, that's why we swung around from the straight asymptote right here and hit that point. Okay, the foci are c units from the center on the transverse axis, which we did. And we use the formula a squared plus b squared equals c squared. So that's just like the Pythagorean theorem. And we do that so we add those together so we'll guarantee that it's outside the fundamental rectangle, inside the curved part of the conic section. Okay, the branches of the hyperbolic curve around the foci and then approach the asymptotes on the end. And we use point slope form, and this is the part that a lot of people think seems complicated. This is what we didn't write over here. We use point slope form, y minus k equals m, and then x minus h for the asymptotes, and we use the fundamental rectangle, the diagonals of the fundamental rectangle, in order to figure out what the equations are. So don't overcomplicate this. Here's what it is. I'm going to grab the y, because that's what it is up here. There's no h, there's no k, it would be 0. Then I'm going to put a plus or minus, and I'm going to put a k, or an x. Okay, there's no h with the x squared there. Okay? And to Crew's question, why did we do this thing right here? We did that rectangle for 2 reasons. One of them is so that we can draw the correct diagonal, so the asymptotes have the right slope. The other thing is to actually figure out what is the slope of that line. So if you'll notice, we went up 3 and we went right 2. So I'm going to do the rise part, that's the y, so I'm going to put a 3 on the top, and I'm going to do the run part, that's the horizontal part, that's with the x. Okay, and this right here, that covers both of those asymptotes by putting a plus or minus in front of it. Notice that this one right here goes down 3 and goes right 2. So they have exactly the same slope. One of them is positive, one of them is negative. Okay, and the rise is always being the square root of the number underneath the y term, and the run is always the number underneath the x term. That is a mouthful.
7th grade stuff right there.
Okay. All right.
Literally preschool.
So, would you take a look at this right here? Do not say anything out loud. I'm going to give you a shortcut for doing all this, or at least keeping track of this long checklist. But I want you to look at this right here. Look at that, and look at the one that we just graphed. What would be different?
I know.
Keely, what do you got?
Wouldn't it open in a different direction?
Would anything else change?
Almost, if you were like,
Other than it opening in a different direction, other than it opening down here and up there, it would open vertically, because the only thing that changed, and watch this,
I don't know, post.
I took the 9 with the y squared, I moved the 4 with the x squared, so we're still going the same amount in the x direction and in the y direction. The fundamental rectangle would look exactly the same. The only thing that would be different is it would run along here, vertice right there, come up here,
Wow.
like this. That would be the only thing that would be different.
And the
by-
foci.
Dude, that looks
And
like a
yes, and the foci would change also along with the vertices. Okay,
Transverse.
everybody good?
that looks like a cool like symbol.
It does look pretty cool. Okay, flip the page over.
Like a spider.
Or we can simply remember.
Okay, you can remember all of that big long list, or you can remember this. We graph hyperbolas just like we graph ellipses, except for the branches open outside the fundamental rectangle. So when I started drawing the fundamental rectangle last week, I didn't tell you that's what it was called, but I draw that so I draw a better ellipse, and so I'm all ready to graph it if it happens to be a hyperbola, which we of course would know ahead of time. Hyperbola is open in the direction of the positive squared variable. We use a squared plus b squared equals c squared to find the distance to the foci, because the foci must be outside the fundamental rectangle so that they can be inside the curved part of the conic section. An ellipse opens on the inside of that fundamental rectangle. A hyperbola opens on the outside, so we've got to add something to that a squared or b squared in order to make sure that the foci are outside. And then this right here is how we write down the asymptotes. So whatever is with the y, we just write y minus k here. Whatever is with the x, we just write x minus h here. And then we put a plus or minus, and then we use the rise and run, the square root of whatever's underneath the y, square root of whatever's underneath the x, in order to come up with the slope. Okay, any questions? Okay, it's a lot. Okay, but take a look at this. Y comes first. This is positive. That means I'm going to have a parabola or a hyperbola that looks something like this. The center of this is going to be, grab the right one, opposite of this, -2, opposite of that, +1. So the center is going to be at -2, up 1. We're going to go 5 units in the y direction. Take the square root of whatever's underneath the y. So I'm going to go 1, 2, 3, 4, 5. I'm going to put a mark like that. Then we're going to go down 5 units. 1, 2, 3, 4, 5. I'm going to put a mark like that. 4 units in the x direction, because the square root of 16 is 4. So I'm going to put a mark like this and a mark like that. And I'm going to take those marks and I'm going to make a rectangle out of them. And this rectangle should be a total of 10 units tall and a total of 8 units wide.
Yes.
And I need to define those asymptotes. So I'm going to go out here and I'm going to draw a dotted line as nicely as I can. I've got some rulers if you want to use them. Okay, and you'll notice that's not perfect. It opens in the direction of the positive squared variable, so that's in the y direction. So I am going to put a big fat dot right there and a big fat dot right there. So I've got a vertex right here and a vertex right here, and the center is right there. And then I'm going to draw what this looks like. It runs along that straight line, that asymptote, and when we get closer to the vertex, we have to come over here and hit that. And then we've got to go out here, and we've got to straighten out along that. Put an arrow on each end. There's the shape we're after. I need the foci, so I'm going to do 25. So I'll change colors again. I'm going to do 25 plus 16 equals c squared. So that's 41 equals c squared. So c equals square root of 41, which is like 6.5-ish.
Exactly 6.4.
So 1, 2, 3, 4, 5, about right here. Okay? So that's going to be the focus, and that's going to be, I'm going to label that point. So it's -2 comma, and we were at 1, and then we added radical 41. So this is 1 plus radical 41, so we were going up that far. And then the one down here, so the foci down here on this lower branch, -2 is the x-coordinate, and then we were at 1, and then we subtracted radical 41 to get down here. So if I were to come back here and say what all these are, so let's see, a vertex, this is going to be at -2 comma 6. That vertex is at -2 comma -4. And of course the center is at -2 comma 1. And then something I notice is that, every single one of these x-coordinates is exactly the same, because we're changing vertical coordinates in order to get to each one of those. And they're also, I'll change colors here, they're also along the transverse axis.
Jack
And does anybody remember what this one's called?
The non-transverse axis.
Conjugate axis.
Good job, Mason.
Okay. Does anybody, can you see, can you look at this and can you tell why they called it the conjugate axis? This is the center, and everything above is kind of like an opposite. So let's take this one right here.
It tells you where the conjugate.
This one is -2 comma 1 plus radical 41, and look at its mirror image down here. -2 comma 1 minus radical 41. You can actually write the 6 and the -4 in the same type of way. It would be 1 plus 4, 1 plus 5, and then 1 minus 5. Okay.
Yeah.
All right. We're missing something.
What?
Yeah.
Asymptote.
Asymptote. So grab this. Y minus 1, put it in parentheses, plus or minus x plus 2. If you can just write that down, you've almost got the asymptotes. All you need to do is remember, how do I make the slope of the asymptotes? This is point slope form. They go through the center right here. The way I make the slope of the asymptote is I figure out how far did I go in the y direction. So find whatever's underneath the y, take the square root, put that right here. It's this distance that you went up. And the number underneath the run is how far you went in the x direction. So how far did we go over here? We went 4, so this would be 5/4. So that, along with the branches and the key features over here, that is a complete sketch of hyperbola. So you can see why people think this is more complicated, but is it that much more difficult?
No, it's easy.
Luke?
Does it make a difference whether or not y minus 1 has parentheses around it?
Not in this case, no, but it's just a good idea. Okay. Any questions? Yeah.
Never mind.
Okay. You're happy about that,
I
aren't you?
liked it.
Okay,
This
take a
is
look at
easy.
the last one.
1, 2,
First
3.
problem is it's not set equal to 1. Graph-friendly form, it's got to be equal to 1. So I'm going to divide everything by 16. So this is going to be x minus 2, quantity squared over 4,
Mic drop.
minus y plus 3, quantity squared over 16 equals 1. Okay, did I get that right?
Yes.
I
Can I-
agree.
Can I challenge everybody right now?
Yeah, let
Don't
us
graph
do
it yet.
No.
Oh,
Write down the equation of the asymptotes.
I already did. Sorry. That is correct.
The
That's the
equation
right
of the
graph.
asymptotes. No, the equation of the asymptotes.
What is that? What's the asymptote?
Oh my gosh.
I forgot, dude. I just do it. I don't think. Don't think, just do.
Wait,
That's
does it
my
matter? Wait,
motto.
I think it
Well,
does.
to do it, you have to.
Or shut up, Jake.
You know, I'll just stay safe and do it the way I think it should go.
Raise your hand if you got it.
Can we do the extreme dot to dot?
Keep your hand up if you want to tell us. Slope. What do you got?
Y plus 3 equals positive negative 2 times.
It's 4.
What
It's 4.
the heck?
Should we see if she got it right?
I'm
So
confident
on the
I
top would be a square root of whatever's underneath the y. That would be a 4. Square root of this would be a 2. And 4 over 2 is 2. So did she get it right?
Yes.
Absolutely. Nice job. Now let's go ahead and graph
Go
this.
team.
So we're going to come over here. The center is at,
don't know what that is.
let's see, 2 comma negative 3. Is that right? 2, negative 3. We're right here. In the x direction, we're going to go 2 units.
Okay, I got that.
In the y direction, we're going to go 4 units.
Okay, I got that. Yes, I got that.
We're going to make the fundamental rectangle here.
I made my rectangle.
What if I don't draw the rectangle and I just freehand?
That's bad.
Oh, you'll probably get wrong. Wilson could figure out not
Well,
You guys are
can't-
so nice to each other.
I
see
love
where, I see
Wilson,
where
but-
the points are, like. Maybe if you're cool,
if I'm cool.
Crew, which way does this open?
Horizontal.
Horizontally. So I'm going to put a dot. Whoops, I'm going to change colors. I'm going to put a dot right there and a dot right there. And I'm going to run along here,
It's basically like, yeah.
straighten out over on the end, run along here, hit that vertex, come out here, and then straighten along there. So I've got a center right here, I've got a vertex right there, and then foci, that's going to be 4 plus 16.
Square root of 20 is exactly
Square root of 20, which would be 2 radical 2. Sorry, 2 radical 5.
4.472135.
Okay, so about 4.5-ish.
Yeah.
So there's a focus, there's a vertex, there's a center, there's a vertex, and a focus would be out here.
Blood do this wrong. Oh no.
Let's see what we got here.
Wait, what is that asymptote though?
2 comma negative 3. Vertex right here at 4 comma negative 3. Vertex right here at 0 comma negative 3. And this would be, let's see, 4, no.
Two,
Take
two.
that back.
Negative, no. Wait a second. No, it's,
Pretty
yeah,
good.
you're right. 4 plus whatever it was,
Oh,
2.
it's going to be this.
Radical 5.
It's going to be 4 plus 2 radical 5 comma negative 3.
That's what I said.
And the other one is going to be, because it's across from the conjugate axis, Still going to be -3. And it's going to be 4 minus 2 radical 2. Sorry, 2 radical 5. Okay, now. Do we have it? Yeah.
Why did you say 4? I put 2.
Oh,
Yeah.
Oh yeah, that's false.
Samesies.
It should be.
it should be, yep, it should be 2. Thanks. That should be 2. Let me get this fixed.
somewhere.
Get my stylus working. Okay, that's 2. Okay, does that look better? Okay,
Yes.
thanks for pointing out the mistake. Okay, any questions?
What's the asymptote?
Okay, we got the asymptotes over there. We got all the key features labeled over here. Don't say anything. Would you look at the 2 of these? What would be interesting about those? Anything interesting? Zach?
It would be a square, not a rectangle.
Very good. The fundamental rectangle would actually be a square because we're going to go the same amount in each direction. This one would go like this, and this one would go like this. Other than that, they'd be exactly the same. I have one more thing I want to point out. We already said Lizzie was right about the slope. Would you take a look right in here? We would rise 4 and run 2. That would be a slope of 2. So rise 4, run 2. But we could also, if you take a look here, rise 2 and run 1. It goes through that point, and that point. So it definitely goes through this center point of 2, -3 and has that slope. So we've got it in point slope form. Okay, now, the only thing I'm going to leave you with is if you want to watch an animation. This is actually kind of an interesting animation. I did not make this. You can't find it on YouTube. So what I did is I made a version of that.
For YouTube.
Yeah, and I just put it on YouTube and gave the person credit
You
for
made
it.
it?
Copyright.
Well, I recorded his.
Credit to DNAtube.com.
How much views does it have? Like 2. What do you think that's 2 pages?
Ah, you got 0 likes, Mr. Laws. I'll get you your first like.
I don't think DNA
we
tube
should
like
make it the most like video on YouTube.
Yeah, I did see they too give you the.